Current estimate for U.S. total electric consumption is 4,137.1 terawatt hours per year. Predict yearly energy consumption in 50 years using a discrete linear growth of 10 to the 6 gigawatt hours per year, a discrete exponential growth of 4% per year, and a continuous exponential growth of 4% per year. So for this problem, the givens are that we have an initial quantity, it's energy, it's terawatt hours, so that's an energy unit. We've got 4,137.1 terawatt hours per year is the energy consumption over the course of a year. In part A, we were given a discrete linear growth of 10 to the 6 gigawatt hours per year. The symbol for the growth factor in discrete linear models K. So that's 10 to the 6 gigawatt hour per year. In B, we were given discrete exponential growth of 4% per year. In the exponential models, that's alpha. 4% is written as 0.04 per year. And it was the same in part C, but that was a continuous, but it's still, the alpha symbol is still used for the continuous exponential model. And then we were told that the time frame of analysis was a 50-year period. And what we were asked to find in this problem was what the total energy will be in 50 years. So the solution methods are, we first need to know what those models look like. The linear model for growth is that the final quantity is equal to the initial quantity plus the growth constant times the number of years. So you can see that's just y equals b plus mx, which is the equation of a straight line, hence the name linear growth model. So we get E in 50 years is going to be Q0, which was 4,137.1 terawatt hours per year. And then we have plus, we want to add on the growth constant times the number of years. So that was 10 to the 6 gigawatt hours and times 50 years. Okay, so we end up getting E50 is equal to 4,137.1 terawatt hours, and we're going to add on to that 50 times 10 to the 6 gigawatt hours. If you do the multiplication out and move the decimals appropriately, you'll find that's 0.05 terawatt hours. So E50 is going to end up being 4,137.15 terawatt hours. So the linear growth model predicts a 0.05 increase, 0.05 terawatt increase over 50 years. So relatively small total increase. B, we wanted to use the discrete exponential growth model. That tells us that Q is equal to Q0 times, I'm writing it incorrectly, sorry there, Q0 times 1 plus alpha, and that quantity is raised to the power of T. So for us, that's going to be E in 50 years is equal to the initial quantity, which is 4,137.1 terawatt hours. We're going to multiply that times 1 plus 0.04. We're going to raise that to 50 years. And so 4,137.1 terawatt hours, we're going to go ahead and multiply that by this. You get 1.04 raised to the 50, which is 7.107. And so the total quantity here in E50 is going to be 4,137.1 times 7.107. That value is a little bit rounded. I didn't do that in my calculator. I carried the numbers all the way through until the final answer, and I got 29,401.06 terawatt hours for the total energy used in year 50. Finally, we want what if we predicted energy growth using a continuous exponential model. So the model there is Q is equals Q0 e to to the alpha T. This is the model most commonly used in the past for energy consumption, although it's kind of not as effective anymore as energy consumption has kind of fallen off in terms of its increase per year. If we were to apply that to this equation, that's E50 again is 4,137.1 terawatt hours, e to the 0.04 times 50 years. And throw that in your handy dandy TI-89 calculator, and you're going to get 30,569.3 terawatt hours as the amount of energy in year 50.